Hello, everyone. Thank you for the very kind introduction. So in the past, at ODSCs, I've spoken at the past few. In the past, I've focused on some of the more advanced, I would say, sexy stuff. I've spoken on GANs and some of the more advanced, exotic deep learning models. Today, I want to focus on a very practical technique for evaluating machine learning models, and that I hope you'll all be able to take back to whatever companies or organizations you're working with and use right away. It's something that I've thought about a lot when working at SentiLink, which is a company I've been working at for the past year. We use this technique all the time. So I'll dive in. By the way, there's a GitHub link here that you can go to if you want. I'll leave it up for a second, but that has the code that will generate the data set that I'll run through toward the end of this talk. And running through this example data set is sort of the fun part of this talk. So, all right, let's dive in. So how do we evaluate machine learning models in general? So when thinking about machine learning models, these metrics that I'm sure most of you are familiar with probably come to mind. You have accuracy, F1 score, ROC-AUC, and all of these are good metrics and important to check. And this is and these metrics are also very popular in research and the cutting edge stuff. So I'm sure some of you are interested in deep learning. Deep learning is extremely cool. And if you followed, what are the best deep learning models, you'll often see which the best ones are by seeing which one has the highest accuracy on, say, a sentiment analysis task. And that's a fine first pass of how good a model is. But today I'll talk about how we can dive a little deeper. And I also want to share, so I heard this quote at a virtual meetup I attended just last week. So, this senior platform engineer at a well-known Bay Area tech company was saying, through a bunch of engineering work, we were able to boost the accuracy of our fraud models by 7%. That's a very common, thing you'll hear people talk about. Overall, we boosted the performance of our model by X% on whatever metric. So what's wrong with this? What is the limitation of this? So let's think about what are some different scenarios that could lead to a 7% increase in accuracy. Oops. So scenario one is there are 7% of your data set, some really tricky cases that before you weren't classifying correctly, that you are classifying correctly now. And this would be a win. This would be the ideal setting. Scenario two is a little bit different. It could be that there are 15% of cases in your data set that you weren't classifying correctly before, that you actually are classifying correctly now. So that's good. But there could be 8% of cases that you were getting right before that you're now getting wrong. So if you think about any end user of your model, whether thinking about sentiment analysis, which is a good generic example I thought of before, thinking of the uses of this. This could be used by Yelp to detect whether, how good a restaurant actually is beyond just the star rating. This could be used by some forum that's trying to keep spam or excessively negative comments off of this forum. And whether or not scenario one is happening or scenario two is happening could provide a very different, could have very different implications for whether the new model is actually better than the old model. So it's very important to know this kind of thing. Scenario three, and this is one that happens a lot in the real world that we see a lot at SentiLink, is, okay, there's 7% of cases that you're now classifying better, but they're all sort of one type of case. So oftentimes what happens when you're building machine learning models is you have a model that's running in production and you engineer some more features. You get a new data set maybe that allows you to better parse out the fraudy stuff from the not fraudy stuff. You engineer some clever feature that helps detect a specific pattern that fraudy people tend to follow. And sure enough, when you retrain your model, oftentimes you'll see that you do better, but just on this one specific population you were targeting. And that's fine, that's good to know. But again, this is very different than scenario one, where just generally, your 7% of cases, you're just better overall. being better in a specific way is very different than being better overall. And this is really important for any downstream users of your model to know. And this, of course, is not just true about accuracy. So I'm using accuracy as sort of my the thing I'm beating up on here, but this is true about if you improve your F1 score or your ROC-AUC, et cetera. The key point is looking at aggregate metrics of how your model is doing doesn't really tell you what's going on. You know, I'll make this point again at the end and throughout, but machine learning models are really complex systems. I think that's the right way to think about them. And to understand how a complex system works, you really have to look at what happens when I feed certain inputs in, like what output do I get? And swap in, swap out analysis, which I'll talk about now, is one way of getting at what those interesting inputs and outputs could be. Okay, so swap in, swap out analysis, as I'll argue, is an analysis you can do that helps you identify what's really going on with your models. And where does this terminology come from? So the terminology loosely comes from credit models, where the in population is people you've decided to lend to. That's just a side note. All right, so what is a swap-ins or what are swap-ins and swap-outs? So suppose we have a classification problem and we've trained a new model, model B, and we're comparing it to model A. This scenario, I'm sure any of you, if you're data science practitioners, have faced. So swap-ins would be observations that model B predicts correctly that model A did not predict correctly. And swap-outs would be observations that model B did not predict correctly, that model A did predict correctly. So in the examples listed above, the size of the swap-in population minus the size of the swap-out population would be 7% of the data set. In the first scenario, we had 7% of your data set swapped in and 0% swapped out. And in that second scenario I mentioned, there are 15% of your data set swapped in and 8% swapped out. I think maybe I can take a question here or take time here. Oh, nice. And see if people have any questions. If anybody posts questions in the Slack, you can feel free to post questions in the Slack channel. Cool, no worries, moving on. Thanks, Naveen, for sharing the GitHub link. All right, so analyzing these swap-ins and swap-outs can help you understand what's going on with your models. So getting more specific, and this is just really, I just want to emphasize, you know, at SentiLink, we spend a lot of time thinking about feature engineering and hyperparameter tuning and many different metrics we track with the overall performance of our models, but we spend a lot of time doing what I'm about to describe, which is actually looking at the cases that have swapped in and swapped out and understanding like what is going on. What are the themes that emerge among these cases that swap in and swap out? So specifically, you know, let's say we have a data set, my code isn't displaying correctly, but you know, let's say we've got our data set and we have model 1 probabilities and model 2 probabilities. These are between 0 and 1. And these somehow map to predictions that are either 1 or 0. Basically, first you want to look at, you can look at model. So let's say the scenario is you're trying to decide, is model 2 better than model 1? Something I'm sure you've all encountered. So fundamentally, you want to say, what are cases that model 2 gets right and model 1 gets wrong? And then the swap outs would be cases that model 2 gets wrong and model 1 gets right. Just writing the pseudocode out here, for those of you that are Pandas users, you'll recognize this. Just doing this analysis, looking at the size of these populations, can give you huge insight into what's going on. And also, I will actually do this later on a data set of NLP tasks and actually look at some of the sentences that swap in, swap out. It's pretty interesting. So first, yeah, you can look at the size of these populations. So this kind of tells you whether you have the 7 versus 0 or the 15 versus 8 scenario from above. Much more importantly, as I've mentioned, so machine learning models are complex systems. If you have a model again that where your accuracy improved by 7%, you should be able to characterize what do those 7% of cases look like. So what are the 7% of cases that before you were not predicting correctly that you now are? Are these cases all new users? Are they cases where, if in the case of sentiment analysis, where the sentence starts out positive and then becomes negative, et cetera, et cetera? Or is it just long sentences, for example? You should be able to give an answer on that. You know, working at SentiLink, if the data science team went to the rest of the company and said, hey, we built a model that's 7% more accurate at predicting fraud, that wouldn't really be enough. We would have to give some answer on, here are some examples of some prototypical examples of cases that before we weren't predicting correctly and now we are. So it's very important to sample these swap-ins and swap-outs and understand what's really going on. And this is something we actually do even more often, is segment these swap-ins and swap-outs based on the label. And so for a regression problem that would be more advanced, you might, you know, if you're trying to predict a value between 0 and 2000, you might look at values where the label's between 1500 and 2000, 1000 and 1500, et cetera. But for classification, it's pretty easy. For classification, you can just segment by whether the label is positive or negative. So for example, your model 2 swap-ins positive would be cases where model 2 got it right, model 2 got it wrong, and model 1 got it wrong, and the label was positive. And the negative swap-ins would be the same thing, but the label was negative. And understanding whether you're doing better on the positive cases or the negative cases also gives you a better idea of what's actually going on. So again, what can you do once you have this? You can randomly look at cases within these groups. You can look at the size of each of these subsets. And this tells you, and this in particular is interesting, and we'll do this on the NLP data set in just a bit. This tells you whether your model's improvement is coming from positive or negative cases, for example. Maybe all the improvement, all of your swap-ins are cases that are labeled positive. That's interesting to know. That could affect the downstream of your model. This is something that we also do, and this is something that you can do without segmenting by positive or negative, but when you segment by positive or negative, it makes a lot more sense. You can look at the worst swap-ins or swap-outs. So the worst positive swap-outs are the cases where model 2 got it wrong, and so the actual label was positive. So for example, the sentiment was positive, or it was actually fraud. And model 2 predicted the lowest probability. So model 2 said, no way this is fraud, or believed it was negative sentiment. Actually looking at these cases and understanding what's going on can tell you what's going on with your model and also give you great ideas for features to engineer. And the worst negative swap outs are similar. You can look at all the cases where model 2, your new model gets it wrong, where the label's negative, and sort where your model's predictions were the highest. Cool. All right, so that's really the idea. If all of you would do this kind of analysis after seeing this talk, if I can convince you that this kind of analysis is worthwhile, then I'll consider this talk a success. It's really as simple as that. I want to illustrate this on a popular NLP benchmark. I actually got thinking about this when I work at SentiLink, and I am also familiar with the deep learning literature. We don't at the moment use deep learning at SentiLink, but again, if you're into deep learning at all, you'll see that, hey, the benchmark for this task is 90% accuracy, but some new model came out that got 95% accuracy. And that'll be touted as some big improvement or big accomplishment. And in thinking about that, I would just ask the question, like, what's really going on there? Like, what do those 5% of cases look like that the new model, this new bleeding edge technique, did better on versus the old technique? And that led me to sort of dig into this myself, and ultimately led to this talk. So what we're going to do is we're going to take a really classic sentiment analysis data set, sort of the most commonly used sentiment analysis data set for benchmarking NLP tasks. And we're going to compare two models on it. We're going to compare an LSTM, which as of 3 years ago was the state of the art on sentiment analysis. And we're going to compare it to Roberta, which is an improved version of BERT, which itself was released 2 years ago and sort of smashed all previous NLP benchmarks. So I don't know how familiar people are with LSTMs, Roberta, and BERT, but if you are, I think this will be kind of fun because to my knowledge, nobody else has really done this kind of analysis, looking at individual cases and understanding, well, what are these cases where Roberta does so much better than the old clunky LSTMs? Cool. So let's have a look here. All right, so first I'm going to import a bunch of stuff. And this notebook is, I'm importing a bunch of stuff from the BERT error analysis repo. So I have my constants, I have a data set reader called sentiment analysis. I have some evaluation functions that are in this module, and I have some stuff here that's in this module. Also, this is a little bit of an introduction to the transformers library. So if you want to do anything in NLP, the transformers library has become sort of the standard. In fact, the links I have above that give you information on BERT and Roberta are to the transformers library documentation. And as I'll say a little bit more at the end, the transformers library doesn't make it super easy to do this kind of analysis. Definitely, I think if I didn't already know what I was doing a little bit and was already a little bit familiar with NLP and deep learning, it would have been pretty tricky to even just get to a point where I was like, you know, taking a pre-trained model, fine-tuning it on this data set, and generating predictions with it. So if any of you, you know, think you have easier ways or have improvements on the code I have here, I'd love to, you know, get a pull request from you, or you can send me some information. But you can. The point is, I hope if you're interested in NLP specifically or the transformers library, you can use this repo as a starting point. You can see how to use it. All right, so let's run that. And basically, I'm going to read in this data set that, well, you'll see. So this data set basically is I'll show it in a bit, but it's all the each row is a sentence, and each row also has the predictions from LSTMs and Roberta. I'll actually jump forward, just do this. So let me actually jump forward and just show you what this data set looks like. Cool. Oh, cool. So this data set looks like this. This is, again, an open source data set. Each observation is a sentence. And these are all sentences that are movie reviews from Rotten Tomatoes. And here I have the label. This is the ground truth label of whether the sentiment is positive or negative. And for a reason I'll talk about in just a second, the labels are either 0 for negative or 2 for positive. And here's the probability of this being a positive sentence from Roberta and the probability from an LSTM. So you can see actually looks like Roberta and LSTM's got all of these right. Some of these sentences are kind of funny, I guess. Like the first one is Schindler's List, it ain't. Let's actually just do this for a second. Okay, I'm gonna ad lib. Okay. So the first sentence is Schindler's List, it ain't. The second sentence is, can you guys still see my screen?
Yeah, no, your screen's fine. You just have some comments in the Slack. I just wanted to alert you to.
Great. Actually, no, I'll keep the, let's go to the Slack. LFF Cynthia, I 1000% agree with this type of analysis. I routinely do these kinds of analysis, and it helped me cut so many bugs and broke my many model accuracy ceiling. Also cannot stress the importance of just looking at the records. Humans' brains just work magic when we see actual records and have a bunch of hypotheses automatically generated. Cool. LFF Cynthia, thanks for the agreement there. Yep. Thanks for alerting me, Jim. Yeah, feel free to keep posting these kinds of things. Thanks for interrupting me, Jim. Cool. So you can kind of see these sentences. So this is the next sentence. This is a positive one. Culkin, who's in virtually every scene, shines as a young man who uses sarcastic lies like a shield. Okay, so both models got that right. Let's look at the second one. Undone by its overly complicated and derivative screenplay, the glacier-paced direction, and the stereotypical characters. Negative. Okay, so all these 5, these are randomly ordered, happen to be ones that both of these models got right. And that's good. Both of these are pretty good models. But now let's look at the ones where they disagree. So here's where it'll get interesting. Go back into slideshow mode. Okay, so first let's actually get what I was talking about. So here are the Roberta swap-ins that are positive. So these are the cases that the actual label was positive, Roberta got it right, and the LSTM got it wrong, et cetera, et cetera. Here's the cases again where the label is positive, Roberta got it wrong, and the LSTM got it right. So this will be kind of interesting to look at. Cool. Oh, I just wanted to make one more quick point. It was interesting learning a little bit about the minutiae of NLP research doing this. One interesting thing is this. So this data set, the entire data set, is about 12,000 observations. And each observation has a label between 0 and 1, like a continuous value for how positive the sentiment is. And it turns out when people actually build these classification models, they ignore any case where the sentiment is between 0.4 and 0.6. So they actually filter out neutral cases. So they just completely ignore them. They don't include them in any of the benchmarks on how well these models are doing, et cetera. So just kind of an interesting hack. You can read the papers, that's the thing. Cool. All right, let's actually look at the swap-ins and swap-outs. This is kind of the thing where it gets interesting. Okay, so first, an interesting finding is that about 70% of the improvement of Roberta over the LSTM comes from improving on the negative cases. And you can check this data set overall is 50% positive, 50% negative. But basically there are 109, there's net like 109 minus 17, whatever that is, 89, 88 maybe. 88, it's, what is that? It's 92. There's 92 cases where, where net on net that Roberta does better on that are negative, and just 40 cases where Roberta does better that are positive. So it's kind of interesting. All right, let's look at some of these. So here are the positive Roberta swap-ins, randomly sampled. All right. So, all right, let's look at 5 of these. So Roberta got this right. The LSTM got it wrong, and the label was 0.7. It is so refreshing to see Robin Williams turn 180 degrees from the string of insultingly innocuous and sappy fiascos he's been making for the last several years. So that is a tough one. I'm impressed that Roberta got this right personally. You have lots of negative words in the sentence, which is probably why the LSTM was confused and got it wrong. You have insultingly, sappy, fiascos. See, and also it doesn't say like, it's not like this movie is different from a sappy movie. Like you have to, the model sort of has to know that 180 degrees means the opposite. So that's, I think that's pretty cool actually. Here's an interesting one. Has a shambling charm, a cheerfully inconsequential diversion. So I think this one's not super positive. I think 0.75 is a little too extreme for this one. Roberta just barely gets this right, and the LSTM gets it wrong. Okay, so that's not super impressive. I guess a little bit. I guess it's not a 0.05. This is not a negative review. Here's a British flick gleefully unconcerned with plausibility, yet just as determined to entertain you. So, yeah, I guess like barely Roberta gets this right, so that's kind of good. This is so far the only one I'm really impressed with. Okay, number 4, evokes a little of the fear that parents have for the possible futures of their children and the sometimes bad choices mothers and fathers make in the interests of doing them good. Wow, so that's an impressive one. I think that this is not super positive like Roberta thinks it is. In fact, it's more closer to neutral. So again, actually, if you look at the distance here, Roberta is not even much closer to the actual value than the LSTM. So again, this doesn't make Roberta look super great. Okay, here's a really good one. It represents better than average movie making that doesn't demand a dumb, distracted audience. So not super positive, but clearly positive. The LSTM gets it very wrong and Roberta gets it very right. So of these 5, I would say the first and the 5th one are like actually impressive. The middle 3 are kind of just okay. So I think that tells a slightly different story than just Roberta gets 8% accuracy from the LSTM on this data set. Cool, so let's look at cases where Roberta got it wrong. These are fun. Okay, the film is just a big, gorgeous, mind-blowing, breathtaking mess. Wait a minute. Oh, well, I think that's ambiguous. I do not think the correct label for that is 0.71. I think that's very wrong. I think Roberta is being very reasonable here by saying this is 0.03. Maybe because gorgeous is in there, this is positive. I do not think this is a 0.71. This is just a messy data set. A pleasant enough comedy that should have found a summer place. That's not very positive. Well, now this is actually making me think more positively about Roberta, because this sort of shows that I think Roberta is not, I think you could make an argument that this is a 0.03 review, and you could make an argument that this is a 0.24. Okay. It's a minor comedy that tries to balance sweetness with coarseness while it paints a sad picture of the single scene. I think Roberta is very wrong here. Like, I think that if you read, like a human reading this is not a really negative review. This is not saying the movie sucks. This is saying positive things about the movie. So that's kind of interesting. If I were, considering deploying this in production, I'd want to look at more things kind of similar to this, and it will actually do this a little further on and understand what was going on there. All right, few films this year have been as resolute in their emotional nakedness. Yeah, I think emotional nakedness, humans know that that's like a positive thing, but I can see how a machine learning model doesn't think that negative. So I also think that's kind of a bad miss. Like, that's not a negative sentence. This one's weird. Message movie or action-packed submarine spectacular. That's supposed to be positive. I think this one should be neutral, so I don't feel bad about Roberta missing that one. Okay, so of these, I think there's like 2 bad misses by Roberta and 2 that are probably mislabeled. Cool, so you could, I hope as I'm doing this, the point really isn't to go super, super deep on NLP and try to understand why Roberta is better than LSTM. The real point is you should do this kind of analysis on any machine learning model you deploy. You should look at the observations that it's predicting positive or negative and try to understand the complex system that is your model. Cool, let's go a little faster through these. Let's just look at the first 3 maybe. All right, so this is where Roberta got it right. Unfortunately, Heartbreak Hospital wants to convey the same kind of haughtiness with its own sketchy material, but this territory has already been explored previously with better aplomb and sardonic wit. Well, that's great. That is a complex sentence and a negative review, and Roberta gets it very right. That is very clearly negative. Good, that's impressive. Oh, here's another very impressive one. When it comes to entertainment, children deserve better than Pokemon Forever. I think that's definitely a negative sentence, and kudos to Roberta for getting that right. Yep. Okay. Never again swings between the false sentiment and unfunny madcap comedy. Swings between false sentiment and unfunny and along the way, expect the audience to invest in the central relationship as some kind of marriage of true minds. Again, very negative. I think it's a very good thing that Roberta says that's negative. Cool. So all these negative reviews, Roberta seems to be doing a really good job on. Of course, if you were actually doing this, you'd want to look at more sentences. All right, let's look at the ones Roberta gets wrong. Nearly surreal, dabbling in French. This is no simple movie, and you'll be taking a risk if you choose to see it. That's very odd that Roberta is very confident this is a positive review. This is definitely not an unambiguously positive review. That's quite weird. So that strikes me as a interesting thing to consider. Okay, the overall feel of this film is pretty cheesy, but there's still a real sense that the Star Trek tradition has been honored as best it can, given the embarrassing script and weak direction. I think that's more of a neutral, because I think that there's basically one positive thing: the Star Trek tradition has been honored, given the embarrassing script, and one negative thing. I think this is closer to a neutral sentence. It's definitely not a 0.9, but okay, I don't feel as bad about that one, whereas that one's a clear miss. A modest and messy metaphysical thriller offering more questions than answers. Yeah, I'd say that's a negative one. And that Roberta, that's not so good for Roberta. Okay, interesting. So there, Roberta has some real issues. I mean, this neutral sentence, neutral to negative one, it very clearly thinks is positive. Cool. Here's another thing I was mentioning before. You can look at the worst cases. So we'll just look at two of these since we're just a little short on time. So these are the absolute worst cases. So these are the worst cases where the prediction was, the actual label was positive, and Roberta said, no way, this is negative. Roberta definitely thinks it's negative. There's not much more to this adaptation of the Nick Hornby novel than charm. Effortless, pleasurable, featherweight charm. Well, yeah, I actually, this doesn't, I think this is like a neutral to negative review to me. Okay, that doesn't concern me too much. It's a minor, okay, we already looked at that one. Yeah, that one's a very clear miss, like very odd for Roberta. Oh yeah, I was gonna, well, I'll look at that one later. Cool. Let's look at a couple of the worst misses that are positive. Still, it gets the job done, a sleepy afternoon rental. So Roberta is very confident this is positive. I don't feel so bad about that one. That could be a positive review. Maybe sleepy, the labeler, if you believe that was negative, I think that's fine. But this one's very weird, nearly surreal, dabbling in French. This is no simple movie. Cool. Just want to share a little bit of an orthogonal analysis. This is something that you can do that's Andre Karpathy tweeted about this. Basically, just look at the worst misses, period. So imagine we never trained an LSTM model and we were just wondering whether Roberta was good or not. What do those look like? So, okay, I think we've already looked at these. Oh, this is great. This first one that's a bad Roberta miss is sarcastic. I think this is funny. When the first few villains are introduced as Spider and Snake, you know you're in for a real winner. Creativity at its peak. So humans can understand that this is sarcastic, but Roberta thinks this is very positive, and so does the LSTM. So this is kind of interesting. This shows that these models can't detect sarcasm at all, which might be extremely good to know if you were going to deploy this on an internet forum, for example, to try to classify positive or negative sentiment, for example. Son of the Bride, maybe half an hour too long, that comes with a flattering sense of mystery and quietness. That seems positive. I'm not sure what's going on there. Okay, there's one other thing I want to make the point about, which is another thing you should do is actually look at individual sentences and just run them through your models and give me just a sec here. And just see what the predictions are. All right, so I was looking at this just before. So I think, so this is interesting. This is one of the worst Roberta misses from before. It's a minor comedy that tries to balance sweetness and coarseness while it paints a sad picture of the single scene. So this just shows, what this example illustrates, I think, what I'm about to show you is how even these bleeding edge NLP models still have lots of cases where they're making like they're easy to trick, or they have weird quirks. So what I think is going on here, the reason Roberta thinks this is so negative is I think that what the author of this review really meant by the word minor is actually rare. It's a rare comedy that tries to balance sweetness with coarseness. Whereas if you take this literally, the author's looks like it's saying it's a minor comedy, meaning like insignificant. And so you can check this out. So if that's your sentence, it's a minor comedy that tries to balance sweetness and coarseness while it paints a sad picture of the single scene. If you change this to rare, Roberta now thinks this is a positive sentence. That's kind of weird, right? If you change it, let's just try different things. Let's do insignificant. So Roberta thinks this is negative. It's a comedy. If you just take that out, Roberta thinks this is negative. It's a comedy that tries to balance sweetness with coarseness. So again, like, it's kind of crazy that just this one word can, and you're not really changing it from a very positive word to a very negative word. Like here, what if you say good? Interesting. If you say good, what about great? Okay, now Roberta thinks it's positive. If you say bad, okay, it thinks it's negative, and so does the LSTM. So very clearly the LSTM knows that bad is a bad word. Yeah, so I think what's interesting is that even these bleeding edge models clearly have some edge cases that people haven't thought about, or that you know, if you were going to deploy this in production, you'd want to think very carefully about. I actually want to try something. Okay, great. First, I'm going to reply to Jerry's comment. While I'm replying to Jerry's comment, I want to say, let's share any sentence and I'll feed it through Roberta and the LSTM and we'll see, and please, nothing offensive, but you know, any sentence here that's appropriate, and we will feed it through and see whether it thinks it's positive or negative. Now let's see what Jerry says. Filtering out the neutrals, or anything between 0.4 and 0.6, seems like it goes against this approach. Don't you want to see if any positive or negative reviews are actually tagged as neutral? Yes, looking at, yes, Jared, great question. Looking at neutral cases is totally a valid and important thing you should do. I excluded them only in this analysis and talk because that's what's done in the papers that, you know, that are written on this specific data set. They exclude the neutral cases from the evaluation for whatever reason. Good question. Cool, so anybody have a sentence they want me to test? Otherwise, I can pull some of these other ones and try to modify them. I think this is kind of fun. So here's one that Roberta got very wrong. There's not much more to this adaptation of the Nick Hornby novel than charm. Effortless, pleasurable, featherweight charm. So let's see. Which of these words does Roberta think are negative? It's not pleasurable. It's not effortless. What if you say heavyweight charm? Does it think it's positive then? No. Yeah, it's not clear why Roberta thinks this is so negative. It's not much more to this adaptation than charm, than substance. Yeah, it's not really clear what's going on here. This, there's not much. How about this? There's not much to this movie. Okay. Except it gets great at the end. Huh. Well, I'm not sure what's going on with this Nick Hornby sense. Anyway, we can keep going with this kind of exercise. I'll quickly wrap up and then take questions. Just want to make the quick point that nobody else really does this kind of analysis. If you take this analysis back to your companies or organizations you work for, you will you'll sound really smart. So this is a very good blog post on LSTMs versus BERT and so on. And in this blog post, they never look at individual sentences. They never say, here's a sentence that BERT gets right and the LSTM gets wrong. Just an illustration of how this is not such a common approach, even though I think it's a very important one. And the Transformers data set, the Transformers library, which is very good, just released a datasets API that, again, is more oriented toward taking in a model and a data set and returning a set of high-level metrics, and doesn't seem to give good support for looking at individual observations and seeing what the predictions are. So I think it's unfortunate that more people don't do this kind of analysis. Since at SentiLink, we do this all the time, and it really determines what we put into production versus not. So just to conclude, swap analysis can serve as an important check on whether an updated version of your model is actually doing better. And more generally, machine learning models are fundamentally complex systems, and the way to build an intuition about how your model is working is to observe lots of input pairs yourself. So swap-ins and swap-outs are examples of interesting input and output pairs. You can construct your own, kind of like I did above. And the key thing is, don't just look at high-level metrics when evaluating machine learning models. Manually test your model on a variety of inputs and see what happens. Cool. That's all I've got. Feel free to clone this repo, reach out to me via email, follow me on Twitter, all that stuff. And I'll head into the Slack channel now for questions. Yes, Ben. Okay, first I'll answer. I don't know if I'll have time to go back up and do these sentences. But first, let me answer LFF Cynthia's question and Ben's question. Can you talk about the next steps? Once we have an empirical understanding of each algo's behavior, what should we do to improve the performance of our AI pipeline? So Cynthia, you brought up, I think, the most concrete thing that we do for this, which is to engineer new features based on this. So if you see that all of the swap outs for a given model are of a particular class, it can be a very good thing to do to try to engineer new features specifically to address those. That's the #1 thing I can think of. I think also just being able to communicate to your end users, whether those are people within your company or users, about what's going on and what they should expect with the model. For example, let's say you're a product manager and you're doing release notes for a model to end users. It's very different to say we have a model that's 7% more accurate versus saying we have a model that is much better at detecting distinguishing this kind of fraud from other kinds of false positives, for example. And then Ben asks, can we get this notebook? I didn't see it in the Git repo. You're absolutely right, Ben. It's not in there. I will add that as well to the repo. Cool, I've got 1 or 2 minutes left. Anybody have any questions?
All right, well, if you want to continue to ask Seth questions in the Slack channel, we'll keep that open. Thanks, Seth, for a really super interesting talk. It was really, and practical too, really enjoyed it. And so we'll end this session, and I hope you guys have a great rest of the conference. Thanks again to Seth for his fascinating talk.
Thanks so much, Jim, and thanks to everyone who listened.
And don't forget to rate him in the survey afterwards, please.
All right, bye-bye.